Good day students, I am Dr. Smita Sharma and today I will discuss frequency response of an operational amplifier. So first of all, the topics that were covered in the previous lecture were practical op-amp. We had discussed what characteristic changes occur when instead of ideal op-amp we use practical op-amp. We had seen that there is an error voltage emerging in the practical op-amp, and we had also discussed the ways by which output offset voltage can be reduced by using certain components. Now today in this lecture we will discuss the frequency response of the operational amplifier. So first of all we will see what do we mean by frequency response. So now up till now we had taken the gain of the operational amplifier as constant, that it remains constant for a longer range. But it should be remembered that it is a complex number which is function of frequency. Therefore, at a given frequency, the gain will have a specific magnitude as well as a phase angle. What does this means? This means that the variation in operating frequency will cause the variation in gain magnitude and its phase angle. So as operating frequency changes, there is change might occur in variation in gain magnitude and its phase angle. So the manner in which the gain of the op-amp responds to different frequencies is called frequency response. Now how can we study frequency response? We'll see that while studying frequency response, certain parameters are considered. A graph between magnitude of gain versus frequency is called a frequency response plot. So the gain, while plotting such a graph, the gain may be expressed in decibel if we want to accommodate a very high gain. Otherwise, it can be taken as a numerical value. Also, the frequency is generally expressed in terms of logarithmic scale, so that a large frequency range can be accommodated in the same graph. The frequency response for the amplifier is obtained from the experimental results. How can we obtain frequency response? We can measure the input voltages and output voltages at different frequency, and then we can calculate the gain, and then we can plot frequency versus gain graph. So this is the experimental method. Another technique that can be used is that is generally used is Bode plot. This technique is generally used in AC analysis of the network. In Bode plot, it is basically composed of two types of plots. One plot is magnitude versus frequency, and another plot is phase angle versus frequency. So what does this mean, phase magnitude versus frequency or phase angle versus frequency? This means that we are plotting a graph by varying frequency and we are studying the respective gain. So change in gain with variation in frequency is plotted as magnitude plot, and change in phase with variation in frequency is plotted as phase angle plot. But Bode plot is an approximate method and is generally used for stability determination and network design. So here basically frequency response for the operational amplifier, we generally use the experimental technique. Now first of all we will discuss the effects that are prominent as the operating frequency increases. So what we are doing, we are changing the frequency, operating frequency of the operational amplifier slowly, and slowly we are increasing it. So what happens inside the operational amplifier? Two prominent effects are observed. First is that the magnitude of gain keeps on decreasing. As operating frequency increases, the magnitude of gain starts decreasing. Second is phase angle of the gain increases. So these two are most prominent effects that are observed as operating frequency increases. So what happens as these two effects start produce are seen in the operational amplifier? So we have said that as operating frequency increases, the phase angle of the gain increases. So as the gain increases, this creates a cumulative effect on the phase shift produced by the use of feedback circuit when op-amp uses a feedback. So what does this mean? This means that when we apply feedback, either it is positive or negative, we know that a phase shift occurs because of the feedback. Now when operating frequency is increased, then phase angle of the gain also starts increasing. So phase angle of the gain also increases, and phase angle is also changing due to feedback. So these two effects adds up, sums up, and the resulting effect is seen in the output. Thus, for a given frequency, the total phase shift between input and output signal is equal to phase shift due to feedback network plus the phase shift due to internal circuitry of the op-amp. This internal circuitry of the op-amp creates phase angle of the gain to increase when operating frequency increases. So due to this phase shift, now phase shift is not only due to feedback, it is also due to internal circuitry of the op-amp. So what happens? At a certain frequency, the total phase shift, that is due to feedback and due to internal circuitry, it becomes 360-degree, and at some moment the magnitude of gain may become unity. As the phase shift becomes 360-degree and the magnitude of gain becomes 1, the circuit becomes unstable and breaks into oscillations. And this condition is we know is Barkhausen condition for oscillations. So this condition is also called a positive feedback. So what is happening now? Under this condition, even though the amplifier is configured for negative feedback, it is actually producing positive feedback. So in spite we are giving negative feedback to the amplifier, but the results that are obtained are showing us the positive feedback effect. So that is not required always. So what is the solution of such a problem? One solution to this problem is very simple, that we should make sure that total phase shift never reaches 360 degrees over the entire operating frequency range of the amplifier. Now how can this phase shift, this condition be achieved? This can be accomplished by using a simple circuit, and these circuits are called compensating networks. These compensating networks are designed in such a way that they control the phase shift and improves the stability of amplifier circuits. In operational amplifier, two main most commonly used compensating networks are phase lag and phase lead. These two are the most commonly used networks. Now we'll discuss the types of op-amp on the basis of the compensating networks. So, on the basis of the compensating networks, we can divide operational amplifier into two types. First is internally compensated. By internally compensated, we mean that there is the compensating network is inbuilt inside the IC itself. So or we can say the compensating network is designed into the circuit to control the phase shift of the op amps. For example, IC 741 is internally compensated IC. Similarly, 351 is also internally compensated IC. So they do not require any external network. The second type is non-compensated or externally compensated. In such externally compensated ICs, we have to apply an external circuit that may include resistors or capacitors, so that are added to a designated terminal in order to work these non-compensated op-amp in a suitable way. So we'll discuss briefly both these two types, internally compensated and non-compensated op-amps. So first we'll discuss the frequency response of internally compensated op-amps. So what does this heading means? This means that we are taking an internally compensated op-amp and then we are changing its frequency, operating frequency, and that results in change in gain. So we'll by graphical representation, we will discuss as the frequency changes, how does the gain of the operational amplifier changes and up to what extent it remains constant and then it starts increasing or decreasing, that we will see. So this is the graph between gain and frequency, gain versus frequency graph of 741 operational amplifier. Now here it should be observed that the gain is expressed in decibels and is in linear scale, and the frequency is in logarithmic scale. This you should see, and this is the graph. Here you should see that for 5 it is by arrow pointer it is written here break frequency, and for 1 megahertz it is written UGB, that is unity gain bandwidth. Now by looking at the graph, we can see here for a gain of 2 into 10 raised to power 5, that is approximately equal to 106 decibels. The bandwidth is approximately 5 hertz. So here this can be seen here. See here for 106 decibels the gain remains constant up to 5 and then it starts decreasing. Gain starts decreasing. So it is almost constant. It starts decreasing before, but it is almost constant till 5. So when the gain is 2 into 10 raised to power 5 or 106 decibels and the bandwidth is 5 hertz, the gain bandwidth product will be simply the product of the two, and it comes out to be 1 megahertz. Now we'll see the other extreme. On the other extreme, we find that bandwidth is approximately 1 megahertz. Here below 0 till when frequency gain becomes 0, the frequency is 1 megahertz and then it remains almost approximately constant. So if here we calculate the gain bandwidth, it comes out to be 1 megahertz. That is, so the gain bandwidth product is constant at both the extreme ends. Now this type of graph holds true for the op-amps like IC741, which have single break frequency. Now what do we mean by single break frequency? Here this single break frequency is represented by F0. Here we have written F0. Basically this is the frequency at which the gain A is 3 decibel down from its value at 0 hertz. So what is the value of frequency at 0 hertz? This is 106, and at 5 what is the value? It starts decreasing and it comes out to be 103. So it is 3 decibels down. So this frequency is known as break frequency. And there are op-amps that have only one break frequency, like IC741, and there may occur op-amps that have more than one break frequency. So this type of condition that we are seeing in the graph occurs only on those op-amps that have single break frequency. So what conclusion we can make from the graph? That the gain of the op-amp remains essentially constant from 0 hertz to F0. This we have already said, that gain almost remain constant till F0, and thereafter it starts decreasing, and this decrease, as we see from the graph, is at a constant rate because this is almost a straight line. So the decrease is 20 decibels per decade. That means 10-fold increase in frequency. As there is 10-fold increase in frequency, the frequency decreases by 20 decibels. This we will see when we will actually work out, calculate these values. Then also we can see it. It is observed from the graph, and then by the mathematical formula we can also calculate it. We will calculate afterwards. So what is finally what can be said, that thus the open loop bandwidth is the frequency band extending from 0 hertz to F0. So what is the bandwidth for such an op-amp? It is simply from 0 to F0. In 741, a 30 picofarad capacitor acts as internal compensating component, which helps to control open loop gain to allow it to roll off at a rate of 20 decibels per decade. So in a 741, internally there is an 30 picofarad capacitor connected to the internal circuitry, so that it allows a stable gain up to up to break frequency, and then it allows gain to decrease slowly at a constant rate of 20 decibels per decade. Now we will see the frequency response of non-compensated op-amps. So again we'll draw the same graph between gain and frequency. Again here in the similar manner it is in decibels and the frequency is in logarithmic scale. We can see there are many graphs showing different values of C, R1 and C2. What are these C, R1 and C2? This can be seen from the figure below. C1 is here, R1 is here and C2 is here. So what are these components? These are externally connected component in order to provide a stable gain. So this is uncompensated op-amp 709, and we have externally applied these components in order to stabilize gain. So the op-amps requiring external compensating components are called non-compensated op-amps. The open loop gain characteristics of the non-compensated op-amps are altered by the compensating components as shown in figure. Now from the graph we can see that open loop bandwidth of 709 decreases from the outermost compensated curve to the innermost. So by applying the values according to values we can see that when C1 is 10 picofarad, R1 is 0, C2 is 3 picofarad, the bandwidth is 5 kilohertz. But when C1 is 5000 picofarad, R1 is 1.5 ohms and C2 is 200 picofarad, the bandwidth becomes only 100 hertz. So by mere using the external components C1, R1 and C2, by applying these external components we can change the bandwidth of the IC. So this IC provides a better opportunity for us uh, to determine the bandwidth. The way how much bandwidth we want to keep, we can decide by using suitable components C1, R1 and C2. Thus, the uncompensated op-amps offer relatively broader open loop bandwidth. So, in this manner, the uncompensated op-amps are better. But for this, we have to properly choose the values of C1, R1 and C2 as shown by the graph. Now we'll discuss that why does this gain of the op-amp roll after certain frequency. That means after certain frequency it starts to decrease at a constant rate. Why does this happens? For this we'll take an internally compensated op-amp and we'll draw its equivalent circuit. Because from the starting we are discussing IC741, here again I have taken equivalent circuit of IC741 that has only single break frequency. So this is basically the equivalent circuit of the IC741. So if you see the diagram, you'll see an additional C is drawn here. This is the equivalent circuit and an additional C is here. So basically what do we say, that the main reason is the presence of some capacitive component in the equivalent circuit of the op-amp, since its reactance decreases as frequency increases. So first and foremost reason that is given for the decrease of gain as the frequency increases is the existence of some capacitor. It is assumed that there is some capacitor that is connected along with that can be plotted drawn along with the equivalent circuit of the operational amplifier. And what does this capacitor do? Its reactance keeps on decreasing as the frequency increases. So because of this decrease in the reactance of C, the gain also decreases. This is the main reason. So what do we do in order to incorporate this capacitor? We draw an equivalent circuit including a capacitor as shown in the figure. Now where does this capacitor, we are saying that we should include a capacitor here in order to, and this capacitor will help us to determine that as this reactance decreases, the output the gain of the operational amplifier also starts decreasing after certain frequency. But where, and for this we have applied equivalent circuit, we have drawn equivalent circuit, and we have put a capacitor also, we have placed in the equivalent circuit diagram. But where does this capacitor originates, from where this C will come, this we can discuss. The major source responsible for capacitance effects are two. There are two main sources. First is the physical characteristics of semiconductor devices, and second is the internal construction of the operational amplifier. So we all know that in operational amplifier generally BJT or FET transistors are used, and they both these transistors contain junction capacitance which have very small value and act as a open circuit at low frequency, but after certain finite value at high frequency, as the frequency increases, the reactance of these capacitors decreasing. So these are the major source that interfere in the operational amplifier. Then the second reason is the internal construction. Now we know when IC is designed, all the transistors, resistors, capacitors are integrated on the same material, and that material is known as substrate, and this substrate acts as an insulator and separate these components, keep these components separate out. They are only linked with the small wiring that is done suitably. So what happens, all these are conducting materials and they are separated by an insulator. So all these materials behave like a capacitor and give rise to stray capacitance. So this is the second reason of C to originate. So if these two effects are combined together, and we have a very certain amount of C in the operational amplifier. This C is represented here in the diagram in form of this capacitor. So this capacitance includes both the effects of BJT FET and the internal construction of the op-amp. These two are combined in the form of C here. So this is single C. This single C is only because this operational amplifier has single break frequency. If it had more break frequency, then the value of C can be more also. Now we'll discuss the relation between voltage gain as a function of frequency. So what we are doing here, we'll mathematically derive it. So again we are taking the same diagram. So first of all we'll apply Kirchhoff's law in the output circuit. So in the output circuit, which circuit we are taking? This one. From here A VID R0 to C in this loop. So we are taking this loop and we are saying that if I current is flowing through this loop, then we can write this equation: A VID is equals to I R0 plus 1 upon j omega C. Simplifying, we can calculate I. Now we'll calculate V0 or V0. What will be V0? V0 will be simply the current flowing in here. With V0 is the voltage with respect to ground, and this voltage is across this C. So we can write V0 is equals to I into 1 upon j omega C. So this we are writing, and we are putting the value of I and simplifying it. So we get V0. Now with the help of V0 and VID, we can calculate the gain, open loop gain. So AOL here, is the open loop gain, and it is considered the function of frequency. So I have written in bracket f. So here you can see in place of omega I have written 2 pi f, where f is the operating frequency. Now if we consider f naught equal to 1 upon 2 pi CR0, then this AOL open loop voltage gain can also be written in this way: A upon 1 plus J F upon F0. So what here we can say that AOL is a complex quantity and it is function of F. So if we define the terms, here A is the gain of the op amp at 0 Hertz. This should be remembered. A is the gain of op amp at 0 Hertz. F is the operating frequency. F0 is the break frequency of the op amp, which is fixed, and it has because it depends on R0 and C. And AOL is a complex quantity and is function of operating frequency. So now what we have calculated here, we have calculated a open loop voltage gain in terms of frequency. So now by the help of this equation obtained, we can calculate as the frequency changes what happens to the gain. So because it is a complex quantity, we can divide it into two parts. One part can be the magnitude and other part can be the phase angle. So we'll discuss both these two parts separately. So the gain can be expressed in polar form and its magnitude will be given by equation 1. So this by the help of equation 1, we can plot magnitude versus frequency plot. Now only looking at the equation 1, certain conclusions can be drawn. First is that at 0 Hertz, if operating frequency is 0, then what happens? This will be 0 and AOL will be simply A. So what does this shows? For any frequency less than F0, AOL is approximately equal to A. And at frequency above F0, the denominator value will start increasing, so AOL will decrease. So as F increases, AOL decreases. All these conclusions are drawn by the help of equation 1. Now in order to test the validity of this equation, we can express this. First of all, we'll change it into decibels. So this is decibel equation. Now in terms, we can also write AOL in decibel in such a way: 20 log A minus 20 log bracket term. Now we can calculate AOL in terms of decibels for different frequencies. So some of the values we have calculated. Suppose F is 0 Hertz. When we place F equal to 0 Hertz and by the help of above equation we calculate, AOL comes out to be 106. At 5 Hertz it comes out to be 103, and so on. For 50 Hertz it is 86, and so on. We have calculated several values. So what does this calculations show? From these calculations, following observations can be made. First and foremost, most important is that AOL is constant from 0 to 5 Hertz. See here 106, and for 5 it is 103. So it is almost constant from 0 Hertz to 5 Hertz. That is first break frequency. Also it is also observed that when F equal to F0, then the value of open loop gain is 3 decibels less. It is 106 here, it is 103 here. So this frequency value is also called minus 3 decibel frequency or corner frequency. After that, it is observed that with every change in 10 folds, the decrease in is by 20 decibels. So AOL decreases 20 decibels each time there is change in 10 folds change in frequency, and at some specific value of input signal AOL becomes 0, and this frequency is called unity gain bandwidth. So for which the unit with that frequency for which the gain becomes 0 is called unity gain bandwidth, and unity gain bandwidth is equal to unity gain bandwidth product only if op amp has single break frequency, otherwise this doesn't happens. Now similar manner we can calculate phase angle versus frequency plot by the equation shown in equation 2. Here we can again put f0 equal to 5 Hz. So the equation 2 changes into 3. Now putting values of f, different values of f, and we can calculate 5 for each case. So these are the different f values, and we have calculated the 5 values. So what we can see that the phase angle varies from 0 to 90 degree as operating frequency changes, and it is also observed that output lags input. Now one thing it should be remembered that when we go through the data sheets provided by the manufacturer, UGB is generally given, and if we want to calculate the F0, that is single break frequency, then we have to use the following equation: F0 barabar UGB upon A. Now up till now we have discussed the operational amplifier that is not using any feedback. So what happens when feedback is applied? So now we'll discuss closed loop frequency response. So in case of operational amplifier, we have seen that open loop gain is constant up to only F0. So bandwidth is also up to F0, and that is very small. But ideally we want bandwidth to be infinite, and gain should be, and for that gain should be same at all frequencies. So in order to increase the bandwidth of the op amp and to make op amp a versatile device, two things can be done. First, negative feedback should be used, and second, it is very important, in order to achieve a stable circuit, the phase angle of the loop gain must be less than 180 degrees when its magnitude reaches unity. If these 2 points are considered, then operational amplifier behaves as a versatile device. It can be used in various applications, and its bandwidth increases. So this is all about frequency response of the operational amplifier. Now we have discussed everything about the operational amplifier. Now from the next lecture we will start the application of the operational amplifier. Thank you.